Welcome back to the Stars and Beyond. In our last episode, we focused on our home, Earth, a blue jewel in space, unique and teeming with life. We explored what makes our planet so special and why it serves as the perfect cradle for humanity. But today, we turn our gaze upward to our constant companion, the Moon. For thousands of years, it has fascinated us, inspired myths, set the rhythm of our time, and ultimately became the first celestial body we ever set foot on. In this episode, we uncover the history behind its name, its geological mysteries, and its crucial role in shaping Earth. We dive into the thrilling space missions that explored the Moon, from Apollo to Artemis, and take a glimpse into its future. Plus, we'll share valuable tips for those who wish to observe and capture it through their own lenses. The Moon, a silent witness of the past and a key to humanity's future. Let's unveil its secrets together. The name of our natural satellite, the Moon, has a deeply rooted linguistic and cultural history that can be traced back thousands of years. The word moon originates from the Old English mona, which itself derives from the Proto-Germanic meno or mina. This term is closely related to Old Norse meni and Gothic mena. The Indo-European root mehans or mens literally means to measure, and highlights the Moon's historical role as a timekeeper. The first calendars were lunar-based, structured around the Moon's cyclical phases. The Latin term luna, from which the French lune and Spanish luna are derived, stems from the Proto-Italic luxna, meaning light or brightness. In Roman mythology, Luna was the personification of the Moon, often associated with the Titan soul, the Sun. In Greek mythology, she corresponded to Selene, while in other cultures, the Moon had its own mythological representations, such as the Egyptian god Thoth or the Chinese moon goddess Chang'e. Interestingly, many languages have words for the Moon that are directly linked to the concept of measuring time. The English word month derives from moon, as ancient timekeeping was based on the Moon's phases. Similarly, in Sanskrit, the term emas means both moon and month. The Moon, our loyal companion in space, has fascinated humanity for millennia. It influences our tides, structures our calendar, and presents us with spectacular astronomical events. Today, we will explore three fascinating phenomena: the supermoon, the lunar eclipse, and the solar eclipse. What exactly lies behind these impressive celestial displays? Let's take a scientific look. A supermoon occurs when the Moon reaches its full phase while being at or near its closest point to Earth, in its elliptical orbit. Unlike a perfect circle, the Moon's orbit is an ellipse with a perigee, the closest point to Earth, and an apogee, the farthest point. When a full moon coincides with the perigee, it appears up to 14% larger and about 30% brighter than an average full moon. This effect is especially striking when the Moon is near the horizon, where an optical illusion makes it seem even larger. A lunar eclipse occurs when the Earth moves directly between the Sun and the Moon, casting its shadow onto the lunar surface. This can only happen during a full moon. There are three types of lunar eclipses. Penumbral lunar eclipse. The Moon passes through the Earth's outer shadow, the penumbra, causing a subtle dimming that is often difficult to detect. Partial lunar eclipse. a portion of the moon enters the Earth's umbra, creating a noticeable contrast between the bright and darkened regions. Total lunar eclipse. The entire moon moves into the Earth's umbra, turning a deep red color, a phenomenon known as the blood moon. This reddish hue occurs because Earth's atmosphere scatters sunlight, allowing only longer red wavelengths to reach the moon. The solar eclipse. Unlike a lunar eclipse, a solar eclipse happens when the moon moves between the Earth and the Sun, temporarily blocking sunlight. This can only occur during a new moon phase. There are three main types. Partial solar eclipse. The moon covers only part of the Sun, leaving a crescent shape visible in the sky. Total solar eclipse. The moon completely obscures the Sun for a few minutes, plunging the surroundings into temporary darkness and revealing the Sun's glowing corona, a truly breathtaking sight. Annular solar eclipse. This occurs when the moon is near apogee and appears too small to cover the Sun entirely, leaving a bright ring of sunlight visible. Due to the precise alignment required between the Earth, Moon, and Sun, a total solar eclipse can only be seen from specific locations on Earth, while partial eclipses are visible over a wider area. The Moon, our steadfast companion in the cosmos, plays a far-reaching and often underestimated role in the Earth life system. Its existence influences fundamental planetary processes and may have even fostered the emergence and evolution of life itself. One of the Moon's most crucial contributions is the stabilization of Earth's rotation. Without the Moon, our planet's axial tilt would be subject to extreme variations, leading to dramatic climatic changes. The current tilt of approximately 23.5 degrees remains largely stable due to the Moon's gravitational interaction. This stability is essential for maintaining Earth's moderate climate and ensuring its long-term habitability. Another essential function is the regulation of ocean tides. The Moon's gravitational pull generates the periodic ebb and flow of Earth's oceans. These tidal forces facilitate the continuous mixing of seawater, which is critical for oceanic currents and the global climate system. Some theories suggest that tidal zones provided an ideal environment for the emergence of early life by creating constantly changing conditions that drove evolutionary adaptations. Moreover, the Moon gradually slows Earth's rotation through tidal friction. Billions of years ago, an Earth day lasted only a few hours. However, due to the Moon's gravitational influence, it has gradually increased to the current 24-hour cycle. This process continues, albeit on an extremely long geological timescale. Even the natural light of the Moon has biological significance. Many organisms, particularly nocturnal species, have adapted to its lunar cycle. The reproductive cycles of certain marine species, such as coral reef dwellers, are directly synchronized with the phases of the Moon. Furthermore, humanity has relied on moonlight for millennia, using it for navigation, cultural traditions, and scientific exploration. Thus, the Moon is not merely an intriguing celestial object, but an integral component of Earth's natural system. Its influences are deeply embedded in the processes of our planet and life itself, and will continue to play a fundamental role in the future. The formation of the Moon is a fundamental topic in planetary sciences and one of the key questions in modern astronomy. Today, the leading explanation is the giant impact hypothesis, also known as the Theia hypothesis. Approximately 4.5 billion years ago, the solar system was still in its chaotic infancy. The young Earth, a hot, partially molten body, experienced numerous collisions with planetary building blocks. One of these impacts would forever change the course of our planet's evolution. According to prevailing theory, a Mars-sized protoplanet, referred to by scientists as Theia, collided with the proto-Earth. The impact occurred at an oblique angle and at tremendous speed. The energy released was so immense that a significant portion of Earth's crust and Theia's mantle was ejected into space. Within a few thousand years, this debris formed a glowing, rotating disk of material in orbit around Earth. Through gravitational interactions and accretion processes, a stable body began to take shape, the early Moon. Geochemical analyses of lunar rocks, brought back by the Apollo missions, provide strong evidence supporting this theory. The isotopic composition of lunar material closely resembles that of Earth's crust, suggesting that the Moon is primarily composed of terrestrial-like material. During its early history, the Moon underwent intense volcanic activity and heavy meteorite bombardment, shaping its surface dramatically. The vast, dark lunar maria, immense basaltic plains, remain as evidence of this geologic past. But the Moon's formation is not merely of academic interest. It plays a crucial role in the dynamics of our planet, stabilizing Earth's axial tilt, regulating climate patterns, and generating tides through its gravitational pull. Without the Moon, our world might look vastly different. Modern research, including high-resolution simulations and lunar exploration missions such as Artemis, continues to refine our understanding of the Moon's origins. Questions remain, such as whether Theia left remnants deep within Earth's mantle, or if alternative formation mechanisms played a role. The history of the Moon is the history of Earth, and perhaps the key to understanding planetary evolution throughout the universe. The coming decades will usher in a new era of lunar exploration. With programs like Artemis, Chinese and Russian moon missions, and commercial ventures, the Moon is set to become the center of astronautical activity. Planned lunar bases could facilitate not only research, but also mining, particularly the extraction of helium-3 for future fusion reactors. The Moon will thus serve as a stepping stone for interplanetary travel and a testing ground for Mars colonization. On a geological timescale, the Moon remains a dead world. Its internal activity has largely ceased, and significant changes are unlikely. However, due to tidal forces, the Moon is slowly drifting away from Earth at a rate of approximately 3.8 centimeters per year. In a few 100 million years, this will make total solar eclipses impossible, as the Moon will no longer be large enough to completely cover the Sun. Over time, Earth's rotation will continue to slow, while the Moon moves into a higher orbit. Eventually, it will reach a point where it can no longer drift away. In roughly 50 billion years, long after Earth ceases to be habitable, Earth and Moon will become tidally locked to each other. A single day on Earth will last as long as the Moon's orbit, meaning the same hemisphere of Earth will always face the Moon, just as the Moon does to Earth today. But long before this tidal locking occurs, our Sun will fulfill its own fate. In approximately 5 billion years, it will expand into a red giant. Its outer layers might engulf the Earth and Moon or expose them to extreme radiation. If the Moon survives, it will continue to orbit a dying Earth around a white dwarf. a ghostly pair in the cold void of space. The space race between the US and the Soviet Union began in the 1950s. In 1959, the Soviet Luna 2 probe became the first human-made object to impact the Moon, followed by Luna 3, which provided the first images of the Moon's far side. Meanwhile, the US developed the Ranger program, capturing high-resolution images of the lunar surface. On July 20th, 1969, humanity made history. Neil Armstrong took his famous first step on the Moon, declaring, "That's one small step for a man, one giant leap for mankind." Over the next few years, 6 Apollo missions explored the lunar surface before the program was abruptly ended in 1972. After decades of inactivity, we are witnessing a renaissance in lunar exploration. China's CNSA landed the Chang'e 4 probe on the Moon's far side, while Chang'e 5 successfully returned soil samples to Earth. India joined the effort with Chandrayaan 2 and Chandrayaan 3, while NASA's Lunar Reconnaissance Orbiter continues to map the surface in unprecedented detail. With the Artemis program, NASA plans the first human moon landing in over 50 years. Artemis 1 tested the Orion spacecraft in an uncrewed mission, while Artemis 3 aims to land astronauts, including the first woman, near the lunar South Pole. The goal, establishing a sustainable human presence as a stepping stone to Mars. The Moon is the next frontier for long-term human presence. Space agencies and private companies like SpaceX and Blue Origin envision permanent lunar bases. These could support scientific research, harness lunar resources, and produce hydrogen fuel for deep space missions. Why focus on the Moon? It provides an ideal testing ground for future Mars missions. Its lower gravity, proximity to Earth, and available resources make it the perfect launchpad for deep space exploration. The Moon is no longer just our celestial companion. It is the key to our future in space. Here are some tips for the visual observation of the Moon. Although a full moon is often seen as the most spectacular event in the sky, paradoxically, it is not the best time for detailed lunar observations. The sharpest contrasts and most visible surface structures appear during the waxing or waning phases along the terminator, the boundary between light and shadow. Here, crater walls and mountains cast long shadows, highlighting fine details. For optimal visibility, an observation site should be chosen that is as free from light pollution and atmospheric turbulence as possible. Elevated locations or areas with stable air, low seeing conditions, often provide clearer viewing conditions. Even a simple pair of binoculars can provide an impressive view of the Moon's main surface features. However, a telescope, especially with an aperture of 80 millimeters or more, allows for more detailed observations. Maksutov or Schmidt-Cassegrain telescopes with a focal length of at least 1,000 millimeters are particularly recommended, as they provide sharp and high-contrast images. Neutral density or variable polarizing filters reduce the Moon's brightness and increase contrast without losing details. Color filters such as green or red can help highlight specific geological structures. Now, here are some tips for astrophotographers. For beginners, a DSLR or mirrorless camera with a telephoto lens of 200 to 300 mm focal length is already sufficient. Advanced users can use telescopes with camera adapters or specialized high-resolution astrophotography cameras. Planetary and lunar cameras with high frame rates, e.g. from ZWO or QHY, offer excellent results through lucky imaging. The Moon is surprisingly bright, so low ISO values, 100 to 400, and short exposure times, 1/225th of a second to 1,000th of a second, are ideal. Overexposure should be avoided, as it can destroy fine details in the bright lunar regions. Stability is essential. A sturdy tripod and a remote shutter release or delay timer help prevent camera shake. Additionally, shooting in RAW format allows for greater detail retention and better post-processing. Advanced photographers can use video recording and subsequent stacking with software like AutoStackert or Registax to enhance details that would not be visible in single frames. This method captures multiple short exposures and combines the best ones to minimize atmospheric distortion. Post-processing is the key to breathtaking shots. Software like Photoshop, GIMP, or astronomy-specific programs like PixInsight help optimize contrast, sharpen details, and enhance color gradations. The Moon, our steadfast companion. In this episode, we explored its many facets, from the origin of its name to its geological wonders and its vital role in shaping Earth. We revisited the historic space missions that reached it, from the first moon landings to the ambitious plans for the future. And for those eager to observe or capture it through photography, we shared valuable tips. But our journey to the stars is far from over. In the next chapter of our series, we leave Earth's influence behind and set our sights on another fascinating celestial body, Mars. The red planet has captivated humanity for centuries, from early telescope observations to cutting-edge rover missions. But is it more than just a barren desert of dust and rock? Could it have once harbored life? Or might it one day become our second home? Join us in the next episode of To the Stars and Beyond as we explore Mars, its dust, its storms, and its secrets.